Hello everyone, I'm Haimin Chen from Nanjing University. I'll talk about competitive class against adaptive adversary in multi-channel neural networks. This is joint work with my advisor, Chaodong Zheng. We consider single hop network with n nodes, any two nodes and neighbors. Each node has reduced with receiver, and they commute over a shared medium containing 3 channels. Time divided into synchronous rounds, also called slots. At each slot, each node either send on a channel, listen on a channel, or remain idling. Only listening nodes will get feedback. There are 3 kinds of feedback. In the single channel setting, in other words, if C is 1, it's determined by the number of sending nodes. For example, if no node send, the feedback will be silence. If exactly 1 node send, all listening nodes will receive the message. When at least 2 nodes send, the feedback will be noise. Back to the multi-channel setting, since there is no interference among channels, so for each channel, its status depends on number of nodes sending on the channel, and only nodes listening on the channel will receive status as their feedback. For example, if 2 nodes send in first slot, but blue node is only one send on channel 2, so the pink node listening on channel 2 will receive the message from the blue node. An adversary called Eve also precipitates the execution by jamming. As long as the channel is jammed, nodes listening on it will receive noise. For example, if in second slot, Eve jam channel 2, and if nodes behave same at first slot, then the pink node will receive noise in the second slot. And the status of channel 1 is not influenced by jamming. Each slot, Eve can jam any set of channels. For example, jam all channels in the third slot. Also, Eve is adaptive, so she's given all past execution history to decide which set to jam in current slot. In results competitive analysis, the only restriction of Eve is the total amount of jamming, whereas the goal of nodes is to complete a task with a low relative cost. Specifically, for each node, sending or listening for 1 slot costs 1 kilojoule energy. For Eve, jamming 1 channel for 1 time slot costs 1. And its budget is denoted as capital T, which is all node to nodes. We seek an algorithm such for any execution, the maximum cost of any single node is at most some function rho T plus some term tau. Here, rho is a function of T and possibly other parameters such as N and C, which capture the additional cost due to jamming. Function tau captures the cost of algorithm when Eve is absent, so tau should not depend on T. The main goal is to minimize function rho, so we consider T is large when compared with N or C. Broadcast is a fundamental communication problem, in which a designated node called source needs to disseminate a message to all other nodes. Chen, Zheng, and Yang proposed first results competitive algorithm. Later, Gilbert et al. Gave a Monte Carlo algorithm that the cost of each node decreases as N grows, and works even N is all node to nodes. They also proved the term soft O of root T over N in cost complexity is optimal up to polylog factors. In our previous work, we considered the multi-channel setting and show having multiple channels available allows a linear speedup in runtime, with the energy cost unchanged, at least for scenarios that N is null. But we also require C should be bigger over N and Eve should be oblivious. In this work, according to whether N is null, we developed 2 algorithms that both tolerate an adaptive adversary and work for arbitrary NC values. The O of TOC term in runtime is asymptotically optimal, since Eve can jam all C channels in the first T of C slots. And the cost remains to be soft O of root T over N. So another question is to put low bound when C channels are available. Another question is to put low bound when Eve is oblivious. All these algorithm group slots into consecutive epochs, execute a jamming resistant broadcast scheme, and check whether to halt after each epoch. An efficient scheme allows each node to learn the message while spending asymptotically less than Eve. For example, in an epoch of R slots, each node only spends little over R, while Eve needs CIRC to disrupt effectively. As for termination, each node counts the number of silences received and compares the number to some threshold. Since a large number indicates broadcast should have succeeded, and a small number indicates Eve had cost much in that epoch. Finally, since nodes does not know T, the usual approach is let the epoch length grows exponentially to get T. So for both node and Eve, the total energy consumption is dominated by that of last epoch. In analysis, we fix an epoch of R slots, fix node U, and found the probability that the U does not hot and the jamming of epoch is weak. For each slot K, then find QK be the set of unjammed channels, and GK be all nodes behavior. When Eve is oblivious, then vector Q is fixed before the execution. So if further behavior in all slots are mutually independent, we can use concentration inequality to bound the following condition probability. However, adaptive adversary can observe nodes behavior. For example, Q3 can be dependent on G1. So condition of fixed Q3, the distribution of G1 is potentially distorted. Therefore, we have no guarantee on expectation of X. Here is our technical overview. First, we consider the easier case that N is null. We show optimal broadcast with proper working property is fast and efficient, reaching the ideal performance for arbitrary values. In its analysis, we partition the event according to the jamming factor capital Q. And for each fixed Q, we use coupling to bound the probability by imagining an execution in which Eve jam ability using a fixed Q. But there are nearly 2 to the RC kinds of possible Q, and the sum of this probability is too large. So we group sectors into R plus C to C categories, and further to R plus 1 categories. When N is unknown, we borrow Gilbert-Law's framework. The analysis needs more effort since we need to group the jamming vector at a final level. This further causes a serious new issue. We fix the problem one by one and derive our second illusion. Here we briefly show our simplest version of coupling. Fix the Q, then imagine a process gamma Q in which N nodes run in a similar algorithm, except Eve jam obliviously using the fixed Q. Here Z is the number of silent slots held by U, and is the sum of independent indicator variables. We want to couple H and C in a third process beta by sharing nodes behaviors. The key point is when the capital Q is equal to the fixed Q, the pair XQ is equal to pair ZQ, according to how XK and ZK are calculated in process beta. Further, event ZQ equals BQ is a sufficient condition to event Z equals B. Since there are too many vectors, we want to group them into few categories. And the vector within one category should have similar effects on X. So in each category, we can couple X using the representative of the category. This is because for each slot, we only care about the size of the unjammed channel set, but not the specific set. Similarly, we only care the times each set is used by Eve, but not the specific jamming vector Q. You can find the full paper in archive. Thank you for attention.